Come again?
On the YouTube video side, the title comes up on your videos. I think that's what you added.
Yes. That's how I get the title. All right, folks. So Pytorch is the dominant framework used to write a neural network architectures. You're all familiar with it. So here is a task at hand, guys. I know that you all have done Pytorch in your previous lifetime. Now is the time to refresh it. Go there. There are tutorials. Very easy tutorials. Good thing about Pytorch is, especially if you have done it, it doesn't take long to catch up. Why should I do it again if I feel I already know everything? Because Pytorch is a fast evolving library. If you did it more than a year ago, you'll be pleasantly surprised at how many new things have come up. There's a lot of things that accelerate Pytorch training. There's a lot of new things that have come up. And if you just look at all of this, you will see that it's a big ecosystem. It also has now support for, well, Torch script, TensorBoard integration has been there for a long time. You will realize that you have support for parallel and distributed training. You have support for quantization. You have support, obviously, for text and vision, no doubt, as before. You have multimodal has come in, right? And recommender systems have come in. These things, like, it keeps getting bigger and bigger and bigger. But good thing about Pytorch is, all things considered, is one of the very well-written code bases. When you step through Pytorch, it should give you some inspiration on how to structure your own neural architecture code. Are we together? As you build it out of the building blocks. The building blocks themselves have been getting simpler and simpler. And frankly, guys, in this world where our instinct is just to go to Hugging Face, download a model, I want you to learn that sometimes you're better off just building a neural architecture from scratch. It is a lot simpler than you think, or than it used to be. Are we together? Right? And I will give you an example of how simple it is. But anyway, before I do that, because that's a fine-tuning part, let me give you the task. How do you create a simple neural architecture? Just go to a quick start, build a neural architecture. How do you build a simple neural architecture? So some things are, almost no-brainer. One of them, let's go through this line by line. Import OS, nothing to do with Pytorch. Pytorch library is imported using import Torch. Torch contains many things, but the main thing is the neural networks. NN is the NN library. Data is loaded using data loader, but there is also the data pipeline, data pipe now, right? Which is a nice thing because you can do a whole set of data transformations and create a data pipe out of it. Very much, somewhat similar to the scikit-learn pipeline, if you remember, right? Or using Spacey pipeline or Hugging Face pipeline. Pipeline is the thing. Everybody uses pipeline.
So the data loader is same as the pipeline.
It's different. Data loader is a piece of a pipeline, but you can put a lot of transformations together as a pipeline. Right? Now, one thing that is a no-brainer that you should always do is this. Device, CUDA, or CPU. And if you're crazy enough to have a Mac, then you can go with the other one in between. No, I'm kidding.
What is it?
Your metal.
You're buying one, right?
I am. No, I don't have a Mac anywhere.
No, he's buying.
Oh, he's buying.
Oh, he's buying an M3, so.
Okay.
That
Yes.
you need
right. I'm kidding, guys.
Having tried
My whole family is Mac, and they feel that they try very hard to teach me Mac. I have been resisting so far. So, all right. So, neural network. Let's give you a refresher on the code. Here's a neural network. This is doing it from primitives. So, what does the flatten in a neural network do? If you get an input, which is a multidimensional array, it will just flatten it. Like for example, a two-dimensional matrix, how do you flatten it? First read the first row, then read the second row and the third row and the fourth row and just go concatenating them. So that's a flatten operation. Now let's look at that. So you take an input and you can flatten it. Now let's look at this thing called sequential. What does sequential mean? Let's draw a picture of a quintessential neural network image that you have in mind. The typical image that you have in mind would be, and at this moment, I'll assume that you have taken the first neural network class. You will create a first layer, L1, isn't it? Layer 1. What does a neural layer consist of? Let's take a neuron, just a refresher. A neuron, actually a layer consists of two things, or a single neuron consists of two things. One is, remember, and this is going back to the absolute basic, neural networks are alternating operations of linear algebra, linear transformations, and deformations. Z and sigmoid of Z. This is not sigmoid, sorry, the activation of Z, deformation function, deformation of Z, let's say, in some sense, right? Deformation. Yeah, these are the deformation functions, or more formally, they're called the activation functions. Why do we need activation functions, guys?
You need to align to the data, automatically align to the data, bend to the data.
The right words, more formally put, why do neural networks need activation functions at all? To introduce non-linearity, says Patrick. Why do I want non-linearity? Why can't I just have a lot of matrix multiplications?
The non-linearity helps you with fitting complex equations within bounds.
Yeah, all of you answered it. See, the point is that if the relationship, ultimately, you are looking at y hat as some function of x. If it is a nonlinear function, right, you cannot achieve nonlinearity through just linear algebra, because linear algebra, so Z is, let's say, the input times some bias term, right? You produce a number. This is a linear transformation. Why? This is just a translation, right? So 5 becomes 7. Shift its value. It's a shift. This is just a shift. And what is this? This is rotation plus stretching. Stretch or scale. W dot x. W is a matrix. What does a matrix do? Matrix, all that a matrix can do to a vector is it can scale it, stretch or shrink it, reflect it, and or rotate it, or do a mix of both, isn't it? So suppose I have a vector, let's say 1, 2, and I multiply it with a number 7, 7, 0, 0. What did I just do? I multiplied the number. This will be equal to what? 7, 14. What's the relationship between these two? 1, 2 became 7, 14. It just got stretched. It just became bigger, isn't it? Because 7, 14 is nothing but 7 times 1, 2. Isn't it? So you just scaled it. The other thing, suppose I do cosine theta, I hope I get my signs right, sine theta, cosine theta of some number, let's say some xy. What is this? This is x cosine theta minus y sine theta, isn't it? X prime is equal to this, y prime is equal to x sine theta plus y cosine theta. What is this? It's a rotation. You just took the x vector, the xy point, and xy coordinates, and then you rotated it by a theta degree angle. Does that make sense? By the way, is it positive or negative rotation? I always get my signs on the off diagonal wrong. One of you please correct me if I got it wrong. But yeah, it rotates it. And all that, whenever you take a point, xy, and it gets to some other point, let's say it gets to this point, x prime, y prime, right? What can you do that? You can think of it as taking this vector in whichever order, let's say shrinking it down first to the vector. So let me say P becomes this vector Q. You can think of it as first it becomes shrunk to R. P to R is scaling. R to Q is rotation, right? So and this journey from here to there is an arbitrary journey mediated by some matrix. So all that matrices do is rotate and stretch. These are linear transformations. There is no way I can take a line, let's say y, z, let's say as a transformation made out of this, all the points along z, let's say that x-axis, right? Is there any way I can rotate and scale this line and that will cause it to bend? Think about it this way. Can I stretch all the points of a line and rotate it by whichever matrices I want, and many matrices, right? Go on stretching and rotating and stretching and rotating and stretching and rotating. Do you think it will look anything except a line? It's not going to look anything except a line. So you need a distortion function. Are we together? And that distortion function is your activation function. For example, if I take every point and multiply it by, let's take the simplest distortion function. I mean, people often take sigmoid and so on and so forth, right? So let's take tan h. Tan hx, what does it do? -1 + 1. Now your function goes, what used to be a straight line, namely, let's take a straight line like this. Right? This here, y is equal to x. It's a line, all points in the line. When you apply tan h to it, it gets bent to what? It gets bent to this. You just introduce a distortion. And it turns out that the moment you introduce a distortion, that's all you need now to have the ability in a neural network to be a what? To be a universal function approximator, right? It therefore now becomes a universal function approximator. That's a universal function approximator theorem. Why is that important? Why should it be a universal function approximator? Yes,
You can model anything.
Yeah, exactly. Like a sufficiently large neural network can now deal with any data.
Exactly. Absolutely correct. And correct, Krishna. See, the point of machine learning is you're trying to discover a function mathematically. All of these knobs and weights and biases and everything put together is a function, right? And if you can approximate any function, you're basically saying, with neural network, I can solve any problem, theoretically, isn't it? And that is why you need activation functions, right? You see the importance of the activation function. It's as simple. See, guys, this field is made up of very simple ideas having overwhelming consequences. Outsized consequences.
So
That's what
the
it is.
neural model can have multiple activation, different types of
Oh,
activation.
Yes.
Yes, of course. You do that all the time, right? And generally, you try not to have too many variations in the activation function. But one simple example is, even if you use a fast activation function in the in-between layers, like ReLU, you'll learn about it on Tuesday. But the last layer, what you do is, you will anyway need something like a softmax if you're doing a classifier, right? So they keep changing.
Asif,
Sorry, go ahead. Yeah, the question is like, so this activation function, so we decide when do we actually decide which activation function that would make sense in the context of, what we're building?
Oh, how do you decide?
$1 million
Activation.
question.
Was that?
$1 million questions.
No. First, you have to be like Dorothy. You have to go to the land of Wizard of Oz and then ask the wizard. So, well, the answer to that is, Prasad, I was speaking allegorically. Just like in the Wizard of Oz, the wizard turns out to be not a real thing, right? In the same way, in real life, we have no way to tell what the best activation function is. It is all empirically decided. Mathematics stays silent at one point. It says so long as you have non-linearity in your activation, it's a universal approximator. Now, if you are taking, maybe I should post that thing. How many good activation functions are there? We know of at least 400 good ones. 400 good ones, right? And you can go on creating more and more of them. Right? Now, since we are spending a moment on the activation functions, they broadly come under two categories. One that have saturation points or asymptotes, as you would say. Like, for example, this has an asymptote. It saturates, isn't it? And the ones that don't saturate at all, or at least in some region don't saturate. For the longest time, people in the neural network community believed that you need saturating activation functions. Part of it, I believe, must have been motivated by biology. This is how your neurons fire, right? This is also the way the transistors fire. Many things, population growth. If you look at how populations in an ecosystem grow, think about it this way. You put a few mice on a little island, right? What happens? There's lots of food. So their population will initially be slow growth. Why? Because, they have to adapt to the environment and whatnot. Soon they'll figure it out. They'll have rapid expansion. And then why will they asymptote? Because ultimately resources will be limited, isn't it? It will become self-limiting after some time. So there won't be enough food to support any more population. So this sort of activation functions have been very common. In fact, the reason one variant of the activation function called the sigmoid, or the logistic function is very popular, but the name has the word e to the minus x, right? The reason it has the word logistic in it is because it was literally the equation used to supply armies with food. Right? And so there's a lot of history to it. But anyway, so long as it has, so good activation functions are either saturating or non-saturating, unbounded activation functions. But the one quality they all have are, A, they are deforming. They must have deformations or non-linearity in them. The second thing is that they must show monotonicity. C, continuity. Let's talk about it. And these things I usually talk about on Tuesday. Non-linearity, now you know why. Well, why do they need monotonicity? It's a good to have. By the way, this is good to have. Good to have, not always. Would you like an activation function that went like this? Right? Go ahead.
I mean, it makes it easier for you to optimize over because you're not unnecessarily introducing like non-convex functions.
That's right. That's a very good answer. That the more complicated you make your function, the harder it gets. But why do you need continuity?
Because then you can't calculate it.
Exactly. No, continuity you need for a simple reason.
Differentiation, right?
No, just the value. You need the value. If it is like this, then what happens if the x value falls here in between, right? So you need continuity for a simple reason. And if you have discontinuity, exactly what will you do here at that particular point? Why do you, then another quality, again, not a must have, but a good to have have is differentiability. Why do you need differentiability? Well,
The
when you do
backprop.
backpropagation, you will need to compute the gradient of the function, right? Gradients become hard to compute if it is non-differentiable. Now, none of these are, like, for example, gradient differentiability is not an absolute necessity because, for example, this is one of the most popular activation functions used quite were the ReLU, right? Which is that, maybe I'll give 1 minute to it. ReLU comes from rectified linear unit. Well, you said linear, didn't we need distortion? Where's the distortion here? Well, you bend the tail and flattened it. Look at the lower half, isn't it? Why rectified? Rectified comes from electrical engineering. There is such a thing as a diode, in which if you give signal input, it will conduct electricity in only one direction. It doesn't go in the other direction, it just doesn't go. Right? So it's called rectified current. So you give it a sine wave electricity, and it will produce only the positive half, right? So that's the rectifier. That's where the word rectified is, because it takes on value only in the positive x space. So why? Rectified linear units, right? And despite the word linear in it, it's linear because in the positive, it's a y is equal to x, right? But there is nonetheless a bend in this line. Now, people have a problem with the differentiability. This is, what if x is 0? What about my derivative? And the answer is, hey, we are computer people. We always fudge. Take it here or take it here, right? Take it in the neighborhood. But then people smooth it out. They often take this, right? And one of the activation functions that's very popular these days is the GILU. GILU, what does it do? It has the word G in it. What could be with G? The Gaussian. Right? So what it does is, if you sandwich the Gaussian function with the ReLU, it becomes GILU. Actually, some of the most of the recent LLMs, if you look very carefully, they use GILU quite a bit. Right? CLU, GILU, but GILU is becoming very popular. Yeah. Go ahead. 1 second. You sort of. No, you didn't tell it.
Do they ever use like a leaky GILU? Because I know that a leaky ReLU is like kind of a thing.
No, leaky ReLU is literally with a little bend.
Yeah.
But GILU by definition doesn't have a problem of differentiability. So why would you have a leaky GILU?
The leaky ReLU was not set to 0 on the other side. It had like a different angle.
Yeah. Oh, slightly. You're right. So you're right. Leaky. Thank you for that correction. This is leaky ReLU, right? This part had a different slope, and this part had a different slope. But I don't know, leaky GILU I've never seen.
Because I know that, I don't know, I guess like in some networks what they observed is that the ReLU, like in general, ReLU is super duper popular because like of its computability in comparison to say like the logistic or the other functions.
Yeah.
Especially 10H is like computationally much more expensive.
Oh yeah, it's very slow. It's very slow. Yeah.
But then they found that like the leaky ReLU in like some networks would yield better results for some magic reason than just having a straight up ReLU function.
See, what the reason for that, actually one reason that I've seen is that even in the negative direction, the fact that the gradient doesn't vanish means the neuron is not completely turned off. That's the main reason. Because if otherwise what happens is in the negative values, the neuron is dead, what people call the dead neuron phenomenon. And you don't have a dead neuron phenomenon. Some information is still passing through. That's the main point of the leaky ReLU. And I suppose, see, all of these, Gaussian just means that you conjugate it, you add, multiply to the Gaussian, right? So it makes sense, because then whatever function it is, for example, a normal ReLU will now begin to look a little bit like that. In most of these cases, what they try to preserve is that, let's say in the positive space, there is no saturation. We learned the hard way that saturation is not a good idea. Right? And what Hinton calls a democracy of values, or equal contribution, equal growth.
Yeah, but also like in most like actual biological neural networks, the reason for the saturation point is not really because there is like by definition there needs to be saturation. It's just that you run out of neurotransmitters like once you fire.
Exactly.
So,
It's the same population dynamic thing.
yeah.
You have only so much of neurotransmitter molecules.
Yeah, so
and-
it's an artificial constraint. It doesn't necessarily have to exist.
That's right. That's right. So yes, some of these ideas that were inspired by biology, later on we are rethinking and saying, not quite a good idea to follow it literally. Yeah. Okay, guys. So now we know about why did we go here. So you have all of these layers in a neural network. Now coming back to code, let's wrap it back to code. So do you realize that at every layer you have a linear unit? Linear unit. What does the linear unit do? It will do Wx plus b, linear transformation, isn't it, guys? Whatever input comes in vector notation, it will do this, right? And then what is the next thing you need to do? You need to apply an activation to this to produce the layer output. That particular layer's output, the output of that layer would be the activation of this. Does that make sense, guys? Right? And so in code, suppose I were to go, look at this picture. It's very intuitive here. You have a layer. That layer internally is made up of a linear and a activation. Right? Let me put sigmoid. Layer 1, activation sigmoid. Whatever output comes goes into layer 2, L2, activation 2. And you can keep on doing it in a simple neural network. Suppose you just do feed-forward network, your classic picture of a neural network. And then finally, suppose you're doing a regression problem and you're predicting a number. In the last layer, how many neurons do you need? One, right? Because it will produce your output. And if you're predicting a number, do you want to saturate it? Or do you want to limit it between 0, 1 or minus 1, 1 or something like that? You don't need to, right? For regression, there is no activation specifically needed in the last layer, is there? There isn't, right? And so what you can do is your last layer is a layer which is just a linear unit with what is the output number of neurons from that? 1. Input is all of them will feed into that, let's say, isn't it? So what you're doing is these are also called sequencers. So there are a lot of synonyms for that. Feed-forward network, linear networks, sequential networks, etc., based on who's writing the library. Now, I can write it as a sequential. Yes.
That first equation Z is equal to Wx plus B, that's a straight line equation that you.
It's a linear transformation, rotation or scaling. Linear algebra is the linear part.
So W is the scale, right?
W is the matrix, the linear algebra matrix. So W is made up of A, B, C, D, let's say, is the matrix. That's why it is called the weight matrix. Weight matrix. Are we together? So let's look at this picture. What will we do here? We'll put a linear unit, isn't it? Linear unit with some input and some output value, right? You have to decide how many neurons to put in that layer. Would you want to do that? Right? Let's say that you want to put 128 neurons. Usually you go by powers of 2, though you can choose to put prime numbers if you so please. Nobody stops you, right? What do you do right after that? You will have to put an activation, right? One of the cheapest activation functions that you can put in, for example, is ReLU, right? You can put a ReLU. ReLU is cheap, though I wouldn't argue that it's necessarily the best, right? Or GILU or whatever you want to put. After that, let's say that you want to build a network. Pick another number for linear. Let's say you want to put 256. You want to again activate it, ReLU, in the second layer. In this particular case, we went straight to the output, just 2 layers, right? So what will you do? Linear, 1. No need to activate. So you would write your code. You would basically, this is a textual description of what your network should look like. Would you agree, guys?
It's a 2-layer.
It's a 2-layer with a third output layer and the input layer.
Sure.
So theoretically, it's a 4-layer network because input is also considered a layer in itself.
Isn't that the second one is much smaller network? 128, it doesn't need to be.
Doesn't need to be.
Okay.
So people can do, see, people go like this, right? Like this. People go like this.
They all trying.
In fact, nobody really knows how to really shape a network, right? There's some mathematical heuristics about it, that tend to work, but it's hard to tell.
So Asim,
So 1 second. So some people make deep networks, some people make wide networks, some people make all sorts of shapes of networks. Right?
so this one pipeline, it's a sequential network, a sequential feedforward network.
Yeah.
So that's composed of first a linear
Linear, yeah,
transformation of 128 nodes,
right.
and then a ReLU for
Yeah.
all those,
Yeah.
and then another linear.
Yeah. So look at this. This is one layer, and this is another layer. Isn't it? Each layer is made up of a linear transformation and a deformation. Now, look at this. This is your second layer, isn't it? And this is your first layer. Literally, 2 layer and then the output layer.
What does it mean as when you assign nodes to this? What happens exactly?
Okay, so when I say 128, what does it mean? 128 neurons are there. 128, and this would be 256.
But you're passing from the weights, like from the linear equation that we had, the WX plus P.
Mhm.
Does it get spread out? Into
Yeah. So let's, since you asked that question, Patrick, let's draw it out a little bit more. Let me, because I can't draw 128. Let's say that you have an input, which is you're trying to, let's take our entrepreneur on the beach. Given a temperature, how much ice cream would you sell? Does that look fair? So input is, X is temperature. Temperature on the beach goes in, right? This input. Suppose I make a neuron of 3 layers, right? What does it mean? It goes to each of these neurons, right? Let me call these neurons 1, 2, 3, right? Now, what do I have? I will have a weight here, W1, W2, W3. So far, so good, guys, right? Now what happens? Here, to each of them, you also inject a bias term, B1, B2, B3, right? What will this produce? Theoretically, first thing that it produces, and that's why you do that, this part, first it will produce, let's look at this, it will produce Z1 is equal to W1 X plus B1, isn't it? Likewise, this part will produce Z2 is equal to W2 X plus B2, and this part will produce Z3 is equal to W3 X plus B3, right? Now, what will come out of this? What comes out of this is, let me put it like this. This comes out as sigma of Z1. This produces sigma of Z2 activation. By the way, by sigma, I don't mean just sigmoid. I mean any activation. Sigma is any activation function. This produces sigma of Z3. Now, let us say in the next layer,
But
how many
all
neurons
the
we want to?
sigmas are the same activation function, correct, Asif?
Yeah, usually you put the same activation function for the whole layer.
You cannot do different activation.
Sanjay says, can you put different activation function for different neurons in the same layer? Nobody stops you, but you have to write the library for it. Nobody has done that, right? So time to create your own open source project.
Because you also talked about network and sub-networks, right? So,
Yeah, you could do that. See, I was joking about it. Actually, you can. What you can do is you can create, let's say, sigma for this one activation function. You can create another network and you can stack it. So theoretically, you can do it. In Pytorch, it's very easy to create a network in which each neuron has a different activation per layer. I don't know if there's a proven benefit to it. Maybe you can try it. People may have tried and learned there isn't much, but you can try it out, see what happens. Yeah. So now what happens is in the next layer, guys, how many neurons do you want? 5. Patrick says 5. 1, 2, 3, 4, 5. So now what needs to happen? Each of these, and I'll just use a fan out diagram, needs to fan to 5 output. And then what will happen? Let me use another color for the second one's fan out. You see that? And let me use a third color, blue, for the fan out of this guy. 1, 2, 3, 4, 5. Now, each of these become input to a neuron. So, for example, this neuron, let me call this neuron, which is of the layer 2, second layer, first neuron, right? How many inputs is it getting? 3, right? It's getting a 3. So now guys, think about it geometrically, what is happening. You took a point on a number line. Temperature was a point in a number line. And what have you suddenly done? You have taken a neural network and that line has suddenly gotten burst out into a surface, into a shape in 3-dimension space. That thing now exists in 3 dimensions. Theoretically, it's a shape in 3 dimensions. Do you realize that? Yes. Right? Because this point now exists in 3 dimensions at this particular moment. And you're feeding it to something, 5 neuron layer. What are you producing now? You're producing another surface which now exists in 5 dimensions. Right? So geometrically, you're projecting it to a higher space and getting a 5-dimensional object out of it. So you have to understand the implication of it. And this is, by the way, my intuition. When I was saying nobody knows how to design a neural network, actually you do. If you think geometrically, you can reason through it. So for example,
this is your line, sir, right? Projecting into the higher dimensions now.
Yeah. Yeah.
Do it like this.
Yeah. So what you do is, suppose you have a page. Imagine that you have a page. So here we go. I'll give you my intuition. Suppose you have data like this. Inside is all blue, right? And outside is all yellow. You need to write a classifier for this. Can you write a classifier? Can you separate the two out with a straight surface, hyperplane in 2 dimensions? There is no slicing of this that will separate the two out. Remember, all of the neural networks, and again, going back to our deep learning theory, what is the last layer of a neural network? It is basically a linear classifier or a linear regressor. Right? They all deal with straight lines and straight surfaces. There is no straight surface that will do this. What do I need to do to this?
Well,
I need to make it into a bowl. Exactly. I need to lift it into a bowl. Right? So that the blue part is at the bottom, the yellow part lifts up. Isn't it? And the moment I do this, now I can make literally a hyperplane, a plane, simple plane that will just slice through this bowl. Blue stay below, yellow goes up. So if I were to solve this problem, what would I do? I would feed this XY data, the input data, X1, X2 data, and the minimum I would need is to feed it through a 3 neuron layer. And the moment I do this, after that, you will realize that you just need one simple neuron to classify it. Do you see the beauty of this, guys? That's how you reason if you're geometrically inclined.
Asif, would you mind continuing that the second layer with the first, showing the linear and the activation function for each of the
Yes. So I will do that. Let me continue the thought. So let's look at this, guys. This neuron, I'll just focus on this neuron, right? Let me call it the neuron that belongs to the second layer and is the first neuron in that layer, right? What is happening there? What is the input it is getting? It is getting sigma Z1, sigma Z2, sigma Z3, isn't it? But each of these can have its own weight. The 3 things can have its own weight, isn't it? Let me call it layer 2, the first neuron, and weight 1. I can multiply it by, because as far as the second neuron is concerned, it's the input. So I can multiply it by, so this is the second layer. 1, 1. A first neuron, first weight of the second layer, first neuron, the second weight, first neuron, the third weight, and plus some bias term, B1 plus B2 plus B3 of the second layer. Would you agree? This would be the Z1 of the second layer, Z2 of the second layer, Z3 of the second layer. Would you agree? Does this make sense, guys? This is common sense, isn't it? And what would happen now when these Z's go through the activation? What will they produce? Oh, by the way, Z4, Z4, Z5. I can continue this. This will become Z. Oh, sorry, no. What did I do? Z2. Yeah. So this is something. Z1 is. I take that back. I did something silly here. No. I misled you. I apologize. This does not make sense. Yeah, I forgot the other ones. What are the inputs here? The inputs here are this plus W1, 2 of the second layer, Z2 plus W1, 3, Z3. You realize that all three inputs came here, right? Green, orange, and blue all went into the first neuron, right? Plus whatever its bias term was. Whatever its bias term was, isn't it? So that is the output of the first neuron in the second layer, isn't it? Do you see that, guys? Huh? Or another way to think of it is, this is nothing but the X that neuron sees, input that neuron sees. Likewise, you can produce the Z5 of the second layer, and that will be W51 sigma Z1, the same thing, plus W52 sigma Z2 plus W53 Z3 Z3 plus the bias term. Sorry. Plus the bias term Z of the second layer, Z5, B5, right? The second layer of the second layer. I'm putting the layers in this funny brackets at the top as a suffix. Does it make sense, guys? It's common sense, right? Yeah. And let us say that at the end of it, you want to feed everything into one neuron. How many inputs is that neuron getting? 5. And plus the bias term. Is it making sense? So do you see how the neurons work, guys? Huh? Right? That is all there is to it. Madhu, is this clear?
Just introduces the
Yeah, I got it. Yeah, this is great.
Yeah,
thank you.
That's right.
So Asil, in the end, finally, we are converting all this multi-dimensional point back into the single dimension.
Squishing it down.
Squishing it down. So first we are expanding in the first layer, second layer, and then we are collapsing back. Collapsing back
because you want a number. So how much ice cream would you sell on the beach?
I know, but why this expansion and collapse? I mean, I'm kind of trying to get the logic.
The logic is exactly that. See, suppose it was a classification problem, and your data was like this. The circle inside is blue, outside is this. So what happens is that ultimately you need a slice to cut it through. Once you have sliced it, right, the only question is upside or downside. Think about it this way. Last layer, right? Look at this problem. Look here. Look at this problem. Here you have projected data into 3D, isn't it? At the end of it, what do you need? You just need to know one slice. And the only question you ask is above or below. That's it.
But make it easy, sir. If you have like 5 different colors and you keep on spending in hyperdimension, in the end you need only one eye in the last layer.
That's right.
You can tell, okay, these are different colors.
That's it. Are we together? That's that. And you could have more. For example, suppose I have to distinguish between cow, horse, and dog based on their weight and size, right? You can choose to have. So let's take the example. You want to write a classifier between cow, horse, and dog. right? So then what you do, all these layers later, what you can do is you can have 3 in your final layer, and you can basically say, whatever the output is, I'll convert it into probabilities, the logits. Remember the logits, the weights, the outputs of the last layer are called the logits. Output of last layer are called logits. Then how do I convert any bunch of arbitrary numbers into probabilities? One easy way is to do it through softmax, right? Softmax, which has some good properties, like it amplifies the big guy and so on and so forth. And they will all become probability of cow, probability of a horse, probability of a dog. And then how do I decide which one of the, is it a cow, horse, or dog? How do I decide now? Whichever is the max. Max. Just find the argument, the class for which the probability is the highest. That's it. So that is all neural network. So now guys, look at this.
And is there a chance of all these all these points, or did you say, can they exist on a 2 dimensions or multi-dimensions?
Oh yes, of course. They can all exist in as many dimensions as you want.
So then,
So one second, let me finish with So guys, remember that between algebra, whenever you see equations, remember there is a geometric counterpart to it. So one easy way that you can think, and this is how physicists think, is whenever you get an algebraic equation, you see functions and these things, ask yourself, topologically, what does it all mean, right? And sometimes there's a very peculiar thing about the human mind. If a problem looks very hard in the algebraic space, it might actually be very easy in the geometric space, and vice versa. I'll give you an example. Many of you remember in calculus, what was the most nightmarish thing that college people go through in STEM field in calculus? They get something like divergence of a curl of a function, curl of a vector is 0. Did you ever encounter this? Right? And you look at this and you're like, prove it. And you're like, okay, now what do I do? Right? But you know what the geometric interpretation of this is? This maps to, this statement is nothing but the boundary of a boundary. Right? So, see, guys, imagine a ball. Look at this. Look at this globe. Right? The earth. This is Earth. Forget about this supporting structure here. This is Earth. This is a solid. Earth is solid, right? The last we checked, we can keep digging. So it's solid. Now, what is the boundary? What is the boundary of this Earth? It's the surface we live on, isn't it? But does it itself have a boundary? Is there a point at which you say, I can't step any further because if I do, I'll fall off the Earth? There's no end to it. You can keep going round in circles, right? So it speaks to the fact that if something is the boundary of something else, that itself will not have a boundary. And try it out. Think for a little bit about anything. Think of a cup. The surface of the cup, the surface, if you're an ant, the surface of the cup, the glaze on it, is the boundary of the material of this cup. You see that, right? But do you think there is any point on the cap, barring gravity, where the ant crawling on the surface can come to a stop and says, I can't go any further? It can keep on walking all over the surface. Speaks to the fact that the boundary, if something is the boundary of something else, it itself will never have a boundary, right? And people say it by the fact that the boundary of a boundary does not exist or is 0. Actually, this peculiar, scary equation that you hit in calculus is just an algebraic formulation of the most obvious geometric fact. You see how it is, right? So, and this is a thing, by the way, a critique that I have of most of the neural network books. They are way too algebraic. When you formulate them in a geometric way, actually, most of the time what they are saying is something very obvious. What neural networks are doing is, and this is what I keep saying, through rotation, deformation, and rotations and deformations and scaling, just take it to a space a different topological space in which it becomes a linear problem, linear regression or linear classification problem. Because that's what your last layer is usually.
It's like Laplace equation, right?
Exactly. Yeah, another example that Krishnan gave is somewhat like Laplace equation. If you guys remember your Laplace transform, what does it do? It converts every differential equation into an algebraic equation. You learn to solve algebra in middle school. You learn to solve differential equation practically never. Right? In college, you struggle with it. But there is actually a transform called the Laplace transform that I don't know why. I suppose they don't teach you early on because then you won't learn differential equations. But after you have learned all sorts of techniques to solve differential equations, finally they mention, oh, by the way, there is the Laplace operator that if you apply to a differential equation, it becomes an algebraic equation. Right? And then you can solve it. So it's somewhat like that, sort of in the flavor. But generally, guys, I find that human beings reason much better using geometry than algebra. So think algebraically. Right? Anyway, so coming back to the fact, guys, now does this equation make sense? Right? This is what you would write. A textual description would be sequential layering. Make a sandwich out of a linear layer, then a ReLU, a linear, a ReLU, and finally whatever it is. Does that make sense? And now look at the Pytorch code. Does it exactly capture that intuition? Look at this, guys. In this particular case, the output layer happens to be 10 for whatever reason. They're just taking an example.
So what's it that is the linear has two parameters?
Yeah, in this particular case, they take the input and the output. But these days you don't. You can just you can have it self-infer it.
Or is it 28%?
Why? Oh, by the way, can somebody guess why is it 28 by 28?
It's multiplied.
This is 5.
So it-
This
No,
is
768. I think.
It's a matrix vector.
What does 28 by 28 remind you of? Think of a data set it reminds you. Okay, I'll give you a dead giveaway hint. What is 28 pixel by 28 pixel?
Different
All the
image.
MNest. Perfect. Perfect. And so the hello world of neural networks is MNest. So now you understand why there was a flatten here. Because it's 28 pixel by 28. So you want to flatten it. So if you flatten it, what will be the length of your vector? 28 times 28, isn't it? So obviously they're trying to do that. Why is the output layer having 10?
10 digits.
10 digits, exactly, 0 to 9. Right? So do you see, guys, how easy Pytorch is? Yeah? With that intuition, does it look dead obvious, this code? Right?
So this is only one cell or one.
No, it's the full network. It's the full neural network.
Of actually just one input. That one input, whichever is
One image will go, yeah.
Yeah.
One image will go and come out like this. But the beautiful thing about neural networks is you can actually give it a Pytorch is you can give it a whole mini batch of the image.
But we are training only one whatever. When we are fine tuning or training this neural network,
Yeah.
we are just giving one input, and then we are
Looking at the output, yeah. Output, yeah. Label data, because your data will always be like that, right? One input, one label.
Oh, I see, I see. So each input will have a different calculation, and in the end,
Yeah.
it will give.
Yeah. This is it. So does this is how you're now look at this. This is how the if you say print model, this is how it will describe itself. Input is 786. Where did 786 come from? 784. Where did that come from?
28 by
28 by 28. Exactly. What is this? What are the hidden layers, sizes? 512, 512. Right? And then what's the output layer size? 10. Right? Now, if you have an output layer and you don't put a linear activation and you don't put any activation in the last layer, what this neural network, the wording you use is, you say it's headless. Because it will produce, what will it produce? The word is logits. It will produce a hidden state of voltages. The way I look at it is arbitrary voltages or logits. It will produce. Yeah. Now what you need to do is from those numbers, you need to produce a probability. Right? How do you take a bunch of numbers and make them into probabilities? Softmax. Right? One of the tricks you can use is softmax, the most common trick. And so after that, do you notice that you give it an input, some random, in this particular case, how do you test it out? you can create a random image. By the way, if you do this and you try to visualize that image, all you'll get is noise, right? Random numbers of shape. What? Why the number 1 in the shape? Yes, just one channel, black grayscale image. So, and 28 by 28 pixel, right? And so you give it to this machine. Actually, it's not just one data point, because these machines can take a collection of data points, right? And
I thought you're supposed to get the 10 digits, and that has to be executed here.
Come again?
You go back to the previous code.
Mm-hmm.
So you have 10 digits there, right?
Yeah, output is 10. No, here we are talking about the input. We are preparing the input.
Oh,
yeah. So you take the input, and if you feed it to the model, and this is the beautiful thing about Pytorch, guys, it uses the Python feature to the hilt. Remember, functions are first-class objects. And what you have defined here is a function. The forward method is implicitly called if you just call the instance, right? So you don't have to call instantiate this and dot forward. You can do that if you so wish, but you don't need to. And so it will return you, when you do the model X, it is the same as calling forward. It will return you certain logics, certain outputs from the 10 neurons. And then you need to convert it into probabilities. Does the next line look obvious, guys? Dead obvious? You're feeding it into softmax. What will you get? You get probability. And then of the probability, you can ask, tell me which one is the biggest, isn't it? And whatever it is, it will tell you whatever is the biggest, right? And then it happens to be that in this particular case,
input is what here?
Input is X, capital X. Do you see? A random.
Some random number.
Some random. Yeah, exactly.
And
picture.
it is saying that
vectors.
Argmax, softmax of that random number, it has predicted, is it?
That noise, that image, 28 by 28 random pixel noise. It says that the best that it looks like is 7. Right. Which would be hard to believe if you actually visualize it.
No, got it, but I'm just trying to understand.
Yeah, guys. Right. So, guys, I'll play around with it. Now, let's break the model down. Now you can look into the fashion MNIST. Fashion MNIST has become too easy for neural networks to deal with. Now, accuracies are 99 plus, way ahead. So then people created the fashion MNIST, which is the new hello world for the 21st century. Right. So fashion MNIST is dresses, people's dresses, again in 28 by 28 pixel, except that it has a color channel, RGB channel. And so this is the input. You can do all of the same thing, neural network. So now, guys, do you understand what a linear layer is and what this thing is?
Asif, I'm sorry, I missed that 28 by 28 thing, and I couldn't follow after that.
It's a historic fact. When MNIST dataset was created by the National Institute of Standards and Technology, they created images of the standard shape of 28 pixel by 28 pixel. Remember, this was created way back when 28 pixel by 28 pixel was considered enough.
Got it. Okay. Yeah. In the case of the exercise that you've given us, it's more of numbers that we're going to deal with. So we don't have to.
So I've given you a simpler problem, guys, much simpler problem in a way, or maybe not. Right. So I invite you now. Do you see how straightforward Pytorch is? In this problem, like I said, the only hint I'll give you is it is a problem that a newbie can solve, and it's a problem challenging enough for a smartie. No more hints.
How many data points, sir?
Arbitrary many. Just go create your training data and your test data.
I said calling again model, you don't need to instantiate class. But just by calling model.
That's it, yeah. Isn't it lovely?
Hey, Asif, I have a question.
Yeah.
So the example that we walked through in this particular one, we just kind of formulated a model, we provided an input and got an output.
Yeah.
We didn't actually do any kind of training here.
No, we didn't.
But in the problems that we have to solve, we have to do some training.
Yeah, I'm getting there.
Oh, okay.
So guys, this is how you get a inference for the model. But if the model is not trained, all the weights and biases are random, it will produce junk, isn't it? Now comes the question, oh good grief, how do I train this model? which is called optimizing the model parameters. How do I train the model? So there is the classic training loop. What do you do? Remember the, hold on. So guys, some of this now, do please come to the Tuesday class. We'll cover it much more systematically. This was very much a do class, but I'll be a little bit quick on it. But I apologize for that because we have to do a lot of things today. We have to do some paper readings and whatnot. But the main point is the fundamental loop of training is this. Let me draw it out. And the allegory, the metaphor that you have to hold in mind is, what would be the right thing? Allegory or metaphor? Metaphor perhaps is better. Imagine that your data is a pile of sand, right? And you're building something in your backyard. Are we together? So you go and you carry your wheelbarrow or your bucket, you go and get the sand. How much sand can you take? The size of your bucket. You take it, you carry it to your backyard, you do whatever you want to do with it, then you come for the next bucket of sand. Are we together? So when you are done with all the sand, the whole pile of sand, and you have carried it to the backyard, you have finished one epoch. One epoch. One epoch is you have visited every piece, every grain of sand. A grain of sand being one instance of data. A bucket of sand being one mini batch of data. For reasons that we talked about in the theory course, it's usually a good idea to do mini batch learning. The two extremes is, if you have a really big truck, you can take the entire sand in one go. Most of us don't have such big trucks at home, unless you do have. But or the other is to go one grain of sand at a time, back and forth. That, you would agree, is a suboptimal approach, isn't it? Right? So stochastic gradient descent is one grain of sand at a time, stochastic learning. The whole pie is another one. And practical thing is to carry buckets of sand, right? So that reminds me of something. I used to tell my two daughters, stories when they were kids. After a little, every day I had to invent one story. So I created a monkey, a red monkey, Dal Bandar. And I would, every day that monkey would have adventures and I would tell some story. But after a little while, sometimes I would be too tired and I would have exhausted all the ideas for the day. So then I would tell them this story. I would say, there was a pile of sugar and one ant came, took 1 gram of sugar and ate it. Then what happened next? Then another ant came, took another grain of sugar and ate it. And then what happened? And I would keep repeating the same thing.
And then they say, no more stories.
Yeah. And by the time I would hope they're asleep, except they wouldn't use substance. Right? So that is stochastic learning. Right? It's very hard to terminate that one.
It's ChatGPT now.
Right.
Better stories.
So that is that's that. So what is the main learning loop? The main learning loop is this. You have a total data that we just call total data, which you usually get from a data loader. Data. So data loader is your bucket. There's a word in this. It's called buckets guard. Right? Whenever you ask it for data, it is sitting upon the whole pile of sand. It will give you a bucket of data or a shovel full of data. So you go to the data loader. So what will be your first loop? First, for number of epochs. For epochs.
1 to 1,000.
Right? Let's say that 1 to k epochs. 1 to k epochs. For each epoch, what will you do? So 1 to an epoch. For each epoch, what will you do? You ask the data loader for data. So in other words, and they have made it very convenient, the API in Python, if you want to enumerate over collection, what do? You literally say enumerate, right? So you can enumerate or you can just say data. If you enumerate, it's your choice whether you want to enumerate, or even if you don't, you can literally say data. But that data, remember, is a mini batch of data. From the data, what can you do now? You can give it to your model data. A Y double star, well, it's a matrix notation. You need to, this is how you pass tensors and matrices to the system. You give it the data, right? Then what comes out of the model? The logits come out, right? Logits. You can convert the logits into, let's say, a probability. Suppose it's a classification problem. You can do a probability, right? Let's say that we are doing digits classification, right? You can do logits, softmax, and you can do arg. Which of these digits was it? So you will ultimately get your y hat, isn't it? What do you do with the y hat now? With the y hat now, you compute the loss. Loss is basically juxtaposing the y to y hat using whatever function you use. Sum squared loss, mean squared loss, then entropy, right? Log probits, log prob, squared loss. These are the most popular, but you have other choices also. But ultimately, you compute the loss from that mini batch. What do you do next then? Given the loss, you can compute its gradient. This will come out of it. Once you know the gradient, what do? You do the update step.
Weight and bias.
Yeah, update the weight and bias, right? So you do that update step. There is only one problem with neural networks. That will, and this has to do again with the theory that I won't go into today, it's for Tuesday. It will only help you do the last layer. What about the layers before that? How do they learn? So there is a magical engine here, which is called backpropagation. There is a whole technology which is called backpropagation, which will make sure that all the gradients throughout the network are computed, right? So that's a bit of a technical detail, but assuming that all that, so there is therefore gradient, and before gradient, there is also the, one second, please. There's also the backprop step. So all the gradients get computed, and then finally the step, update step, update, which is the actual gradient descent step. I'll take questions in a minute. Gradient step. So now what happens at the end of it? What happens? All the weights and biases in the network are updated, right? So when you do the same operation again now in the second round with the next mini batch of data, this is the new starting point. The network has changed. It has learned. You say it has learned from the mini batch. So gradually, as you keep doing mini batch after mini batch, you will exhaust all the mini batches. All the sand will be gone, right? And now, unlike real life, when all the sand is gone, what happens? You have no more sand to get in. But imagine that all you were doing with the sand is, the moment you bring it in, magically, all the sand goes back outside, right? So, you know the story, I believe it's the Greek mythology, is the story of Sisyphus, right? Yes, who has to keep, his punishment is, he has to take a big boulder and keep pushing it to the top of the hill. And the moment he does that, it comes rolling down, right? And he has to start all over again. So such is your fate. Your next epoch is carrying this big thing, the sand, all over back to the backyard. And the moment you're done, it magically all shows back into the frontier. So that's your next epoch, right? So you keep going this, and so you have two loops, inner loop and an outer loop. Inner loop is on mini batches, outer loop is on the epochs, right? So outer loop is the, did I say it right in the Greek word, Sisyphus? Is it correct? P-H-U-S or P-S?
I think it's Sisyphus, like P-H-U-S.
P-H-U-S, yes. Sisyphus. The Greek story of Sisyphus. That's it. The outer loop is the fate of Sisyphus. You start all over again. Except that you terminate. Unlike Sisyphus, here you do terminate after a certain number. Yes, you have to do it well enough. So what should you do, guys? How do you know? The question that it raises is, How many epochs are enough? How do you know? What's the empirical evidence that you're actually learning anything whatsoever?
The last function is.
Yeah, see, remember what is measurable here, and this is the question you always ask in empirical sciences. It is not a science unless you have something empirically measurable. Loss is measurable. And so each step, each inner loop that you do is step, each outer loop that you do is epoch. For heaven's sake, make a plot of steps is good, or epochs. Usually you take steps and the loss. And what will happen? Your loss will show a saturation. You're not learning anymore from this. Are we together? So when do you stop? Unless you have a hardware constraint, you stop when the loss saturates. Or sometimes you stop a little bit early. Sometimes what happens is if you suspect that your machine may overfit the data, you may do early stopping sometimes. But generally, the basic rule is you wait for this asymptote, or more colloquially, saturation. Does this agree with, this is common sense, guys, huh? Isn't it? Right? This is it. Let's see where in Pytorch this code is, or should I leave it as a minor exercise for you guys to hunt it out? Optimization loop. So now look at this, guys. Now, there are various kinds of optimizers. You will learn about it not in this course, but in the Tuesday course, which I highly recommend. If you're not there, do it. No, but I'll leave this there. So look at the training loop, guys. For batch in XY, enumerate data loader. Now, does it make sense? Who is the data loader? The giver of buckets, isn't it? What is the batch? Here, the word batch stands for what? It is the batch count, the step integer, 1, 2, 3, 4, 5.
Many batches, stochastic or the batch.
Yeah, batch size. No. In this particular case, the word for batch and XY. X and Y are simple. The input and the ground truth, right, of data. Because when you get the data, it will give you, okay, this is the input, this is the ground truth that you expect, right? But batch is just a count. First batch, first bucket, second bucket, third bucket, fourth bucket, fifth bucket.
So basically the steps.
Steps, basically, right? In fact, if you notice that I tend not to use the word batch, I tend to use the word step count or step, or index or something like that. Now look at this code, guys. Tell me that it makes sense. What do you do with the input? You feed it to the model to get the prediction. In this case, the model is not only doing the logics, but it's doing the internal softmax or whatever it is supposed to do. Is this your basic loop? From the prediction, what do? You'll compute the loss. For loss, you'll use a loss function, whatever the loss function is, cross entropy loss, negative log likelihood loss, mean squared loss. All of these things I've taught you guys in different courses. What do you do after that? Once you have the loss, you need to compute the, what about computing the gradient? Where did it go?
So what is the initial weight by us? It's not clear.
Oh, you randomly throw something at it. Where did my computing the gradients go, guys? What happened?
Gradient. Yeah, with the zero.
Optimizer zero. Okay.
No. That will nullify all the gradients.
Oh, okay.
Oh, where did the gradients go? And that brings to one of the most powerful topics and virtues of Pytorch. Pytorch belongs to a class of libraries which does something called autograd or auto-differentiating libraries. Whenever you compute a function, so this is a point that I should mention, is a very important point. See, typically when you write a function, f, def, f, right, whatever, x, and you say return x squared. Suppose you define a function like this, right? You give it an input, what will it do? It will return you a x squared. But there are certain frameworks which gives you as a bonus, will not only compute f, but it will automatically compute df dx also and store it. Or more in multivariate, it will compute the gradient of f and store it also. So every time you ask it to compute the value of a function, it will compute the gradient also. So what does it mean? As the data flows, input flows through these layers, remember those activation functions are there. The moment you feed z into the activation function, what does it also do? It computes the gradient of z. You would say, well, how in the world does it do that? It's quite simple. For example, if you have, let's take logic, sigmoid function, sigmoid. Sigmoid x is what? Sigmoid z is what? Sigmoid z is this, right? So let me just say sigmoid. What is the derivative of the sigmoid? As is obvious, it is 1 minus. I'm sorry. Is this obvious?
Yes.
Okay. Okay. I'll give you guys the proof for one. Okay. Okay, guys, I'll give you the proof how to prove it. Oh, by the way, this is a proof that's given, and the reason I'll give you the proof is this proof is often mentioned in a lot of textbooks on neural networks. And instead of explaining anything, it just ends up scaring the students, right? So I'll give you a dead obvious proof. So when I say as is obvious, it will look obvious to you. How about that? I claim that I can make it look obvious to you. Do you want to see how? Right? See, this function, sigma x is equal to, sigma z is equal to 1 plus e to the minus z. This is the function, isn't it, guys? I can rewrite this function by saying sigma z 1 minus sigma z is equal to e to the z.
Okay.
Right. Now think about it. Sigma is suppose a probability, right? It's some probability. This is nothing but p over 1 minus p or p over q. Do you guys remember what this is? Log odds. Sorry, this is the odds. When people say, oh, this political party is likely to win over this political party, or sports people will say this team is likely to win over that team. They don't talk probabilities, they talk odds. 1,000 to 1 odds that it will win. What are they? They are the ratio of probability of winning over losing. So this is nothing but odds, right? And what you are basically saying is that the odds is e to the z. You can work out this equation. How do I go from here to this statement? It's very easy. Just do this. This thing, and this is one of the things that you forget. See, there was an old British book. I don't know if you guys remember. Called Hall and Knight's Higher Algebra. Does that ring a bell in anybody's mind? You guys are too young.
We didn't read it.
Okay. It's an
Yes.
old British book.
Yes, all at night.
Sachin, you remember that,
Yes,
right?
yes.
No wonder you went to IIT.
We didn't even know that.
Okay. So here's the thing. The trick is if you have a number, let's say any number, if A is equal to B, A over B is equal to C over D, right? Here is a statement that will also be true. A plus B over A minus B is equal to C plus D over C minus D. This also will be true, right? You can prove it. And that guy who wrote that Brit who wrote that book, he used to call this method componendo and dividendo. Must have come from some Italian trick. But anyway, you can convince yourself. I won't go into that, but see, if I have sigma is equal to 1 plus e to the minus z, you would agree sigma is sigma over 1?
Yeah.
Isn't it?
Of course.
That part is obvious. Suppose
That is the only
That we can understand without copy.
right. And now you can reverse this thing. You can say 1 over sigma is equal to 1 plus e to the minus z, right? Over 1.
Yes.
So far, so good?
Yeah.
Right. And now, what happens if I, and by the way, this whole problem gets much simpler. If I multiply everything by e to the z, you would agree that this is In fact, becomes even easier.
Yeah.
Plus 1,
Yeah.
right? Sigma over this. You agree this part is true?
Yeah.
Right? And now from the denominator, subtract the numerator. It will become 1 minus sigma, and this will become minus e to the z. You agree?
Yes.
And therefore, as it becomes obvious, sigma 1 minus sigma is equal to e to the z. That's all, because this and this cancels out. Isn't it?
Yes.
So you can literally stare and see the obvious. And once you do it, you say, oh my goodness, there's an e here. So I can take the log, and then this becomes z. That's why this term is famously called the log odds. Famously as in the small group of people who see it as what it is, right? And so this logic function would have been so much easier written in textbooks, but isn't for some reason. If we just wrote it as this, sigma log odds is equal to z. That's all that this activation function is saying, isn't it? Now look at the log. By the way, what is the derivative of a log? What is the derivative of log x? Come again. Derivative of log x is? Please. Log x. What's its derivative?
X.
dx is equal to 1 over x. Okay, Yeshila is the only one who remembers the calculus, right? So suppose I take log, so suppose this quantity, right? Let me just call it as theta. Suppose you have log theta. What is d dx of log theta? It is d log theta with respect to theta, d theta with respect to x. Does it make sense? No. Does it make sense, guys? Obvious, right? So there you go. Now, what is, and therefore, this is 1 over theta times d theta dx. Right? Now, look at this equation. Log sigma 1 minus sigma is the same as log sigma minus log 1 minus sigma. Right? And so when you take its derivative, this will become 1 over sigma times d sigma dx. Am I making sense so far? And this is negative here. And when you do this, this will become positive 1 over 1 minus sigma. Right? Again, d sigma dx is equal to, what is the derivative of, well, in this particular case, it was z. So I'll just make it z everywhere. And what is the derivative of z? Derivative of z is dz. What is dz? 1, isn't it? And therefore, you come to the very obvious conclusion that 1 over sigma plus 1 over 1 minus sigma d sigma dz is equal to 1. Right? Do I need to correct the dots any further? By now it's beginning to look obvious. Now d sigma dz is equal to sigma 1 minus sigma. Right? You see how obvious it was? Right? So see, guys, this comes through experience. I really mean it. I don't know, for some reason, the interpretation in computer science books or neural network, this derivation is almost never given. It's given in a very complicated way, usually. But it is literally as simple as this. Right? And there's a lovely property with this. For example, tan h, z. What is the derivative with respect to z of tan h? Oh, goodness. It is actually, as is obvious, 1 minus tan h z, 1 plus tan h z, which is the same as 1 minus tan h square z. You can convince yourself. Very similar, same component to dividend argument. Adding the numerator to the denominator, etc., will convince you that this is it. So anyway, the point is, if I know a function, what is the point that I'm harking at? If I know the activation function, I usually know the formula for its derivative. It is just another function, isn't it, guys?
Yeah.
Derivative is just another function. And so an auto-differentiating framework may choose that every time you compute the function, I can also compute sigma 1 minus sigma while I'm at it.
So what do we need to worry about figuring out gradient descent for the activation?
Because now you know the gradient, and so you can do gradient descent. Right? So remember,
but we are doing it on the sigmas, on the activation function.
that's the output. Yeah, that is your function, because that local learning is with respect to that activation function.
Okay, so you're fine tuning the activation function.
Yeah. So we'll come to that. So I'm giving you guys a flavor of that. Right. So guys, these frameworks are called self-differentiating frameworks, or auto-differentiating, or autograd frameworks. So that explains why we don't see. Now you understand why we don't have a compute the gradient. Right?
So
It's already done.
So the next batch already has it.
Yeah. So guys, hold on. I'll come to you, Prasad. I know you have been holding a question for a while. So guys, remember, typically, you do it, you'll see the difference. If you were doing it in NumPy, what would be the only difference? You would compute the gradient yourself. Right? So you would have to know that little bit of arithmetic. That's the only difference. It's a convenience to not have to do that. Backwards is the back propagation. What is the optimizer dot step? Gradient descent step is the gradient descent step. And then finally, you do optimizer dot zero grad. Why? It's a library requirement. They want you to wipe out the slate.
For the next batch.
For the next batch to learn. That's it.
Okay, that's the trick. That's what I wanted to know. Then update how it will see. It has to know the previous numbers also, right?
Yeah.
Otherwise, when you are zeroing, then you are restarting with a clean slate.
Yes, exactly.
Okay.
That is it. And so you notice that in this code, very helpfully, they have batch is equal to every 100 batches, every 100 steps, they produce the loss. Isn't it? They're printing out the loss here.
Yeah.
And that is important.
Without someone explaining, how can we understand this code?
Without someone explaining, how can you understand the code?
code?
Thank you for saying that. It means I'll still have students in the future.
Job security.
Job security for my business. Right. So guys, now here comes the important part about Pytorch. Remember guys, autograd is on by default. But do you want your gradients, do you want your weights to be updated, a learning to take place during inference time? You don't. Not only that, even if you don't do the learning step, do you want the gradients to be computed? It's an overhead, right? Remember, gradient computation is more expensive than generally, and backpropagation are very expensive operation. So what do you want to do when you're testing, when you're evaluating? You want to explicitly put the model in evaluation mode, which simply means that gradients will no more be computed. Backpropagation. It is not ready to do all of the learning, right? It is important, and you should call model.eval. Unnecessary in this situation, but added for best practice. I would say necessary. Why waste compute resources? Right?
So what model.eval will do?
It will freeze the, it will just freeze, it will keep the weights,
the-
it will just not compute the gradients anymore.
On the update.
No more gradients. It doesn't need gradient because when you're making prediction, you're just going in the forward direction. Isn't it? See, look at this loop. When did you need the gradient? For the optimizer step, for the gradient descent. Right? Gradient descent is a learning step. You need it only during the learning process. You don't need it otherwise. And so when you're doing that, you turn it off and then you go and do test and loss. The rest of it, guys, I hope is obvious, right? When do you use a cross entropy loss or these kinds of losses? When? Yeah. Now look at this values, the loss propagation, guys. Do you see that the loss, what is it? Is it decreasing or increasing? Or what is happening to the loss? Decreasing, but not always. Look carefully. Right? The reason is whenever you do mini batch descent, you're taking batches of data. It contains not just information, but noise. Right? So what will happen is with mini batch, it will always make small perturbations around the correct parameter values because the noise is perturbing it. Isn't it? That is it, guys. Epoch 2 And finally, you go to look at the different epochs. And finally, well, it seems as though 0.79, you ended with this. If you look carefully, it actually achieved lesser loss somewhere here. In fact, even less somewhere here. Are we together? Right. But you don't mind it at some point. Well, this is a simple example. You don't mind it. Right. So guys, that is it. But when you build a model takes time to train. You want to save the model. How do you save the model? Model is nothing but a matrix, a tensor, multidimensional matrix of weights and so forth. So you can save the model states into a dictionary. Are we together? Do that. Pytorch. You can save it as a Pytorch dictionary, and then you can load it back from the dictionary. The model.load. So these functions come. How in the world did those come from? They came from the base. You notice that you start your neural network by inheriting from a class called nn.module. Right? Those things are built into the module class. Yeah, those are God-given functionality for you as far as you are concerned, and it comes built in there. Right? Right? These are the functionalities that come built in. So that is it, guys. That's Pytorch. I leave hugging faces for next time, but I hope that introduction was useful for you to get started. Build your model from scratch, guys. And now let's go revisit this question. I hope it's dead obvious how to do this homework.
Data mean deviation, standard deviation.
Yes. So guys, I deliberately posed a problem for which there are not a bazillion solutions on the internet, right? It will make you think. The whole point is to write code. I wanted to give you a problem. I just thought of it as we were talking, but I crafted these problems, and I gave you a stretch goal also, that see if you can train the network. First, that you must do A and B, you must do for classification. Is any of them negative? Tell if any of the numbers are negative. The second is if the sum is greater than 100 or some number, whatever number you want. And finally, a stretch goal, does any of them look like a prime? Any of the inputs look like a prime? Remember, you can't do math. You have to make a neural network come up with the answer.
One question, maybe you don't need to tell the answer if you don't want. So all the training independently train, or it's like,
No. Each of them is a different neural network. Each has to be trained differently.
Exactly.
So guys, I must say, it is not one neural network doing all three jobs. It's not that versatile. Yes. Make a neural network for each of them.
Yeah, I was confused. No, it's good.
And regression, very similar. Find the total, predict the average and the standard deviation. And while you're at it, find the max. What is the max? Which of them is the max?
So we are talking 3 neural, one for classification, one for regression.
6. We are talking 6 neural networks.
Okay.
So we have classification problem, we have regression.
Yeah.
And then find any prime number and then see what.
If there's a prime number present, true, false.
So 3 different problems.
Yeah. And then regression is find the total, predict the average, standard deviation, max. So guys, it is important. We are doing it on LLM, but at the end of it, you need to know how to create a neural network from scratch. Now we will go to pre-train, the fine-tuning, guys. We'll take a 5 minutes break and we'll change topic to fine-tuning, but we'll start with a research paper reading. Today, guys, you'll be here till 10 p.m. Ready? 10 p.m.? Okay, good. Good.
Yes.
Are you having fun, guys? Is it fun so far? Good.
In that model training function earlier, you don't need to return any value. I didn't see any return from the.
No, it's automatic. Let's go back to the code. look at this. The train part. Where is the train part? The model input produces output. It always produces the logics or the probabilities.
Right. So we're assigning. So by running the model, we'll produce the logs. But if you go down,
No, this is not the training loop. Let's go to the training loop. Let's get this training. Yes. This is your main training loop here. Where is the main training loop? Sorry. No. Yeah, fully. This is
like the first function, train.
Yeah, model. Unnecessary. This is no. That dot train just says enable auto differentiation. That is it. It doesn't actually train. It just says I'm entering the training. It's a very badly named function. It should say right. Set train mode or something would have been better.
Sure. So it's just saying that from that model class that we had defined the sequential to perform this train method, and then on my batch that I predefined as number like 100, and this tuple is just your data set of the train test. But and then it performs all the steps per batch. But where's the part where it returns?
At the end of it, it's just internal weights and biases. That's it. So you have to save the model. That is why once you have trained it, you better go save the model. Saving the model is the next topic in this.
Yeah.
Like, can you go back?
So in the end, it's optimizing.
See, as it says define train loop, right? And it takes data from data loader.
Yeah.
It takes the model that you set as sequential.
Yeah.
It takes the predefined loss function you set.
Yeah.
You optimize.
That's it.
But where's the return? Like,
no, it doesn't need a return. You give the model. The model's internal state has changed. This weights and biases have changed.
So it's just following. So okay. So you're taking the whole.
Yeah.
Okay. And then
that is. There's no need to return anything. But the model that came in is not the model that goes out.
So if I wanted to train two models in parallel, I can't do that.
Why would you?
Because if I call train loop.
Yeah. No, it's independent. Just fire off a different loop.
That's fire. Okay. So it will just instantiate again.
Asif, can I make a suggestion?
Special data distribution.
1 second. Sukhpal is asking a question. Go ahead.
As he was saying, sir, for data distribution, activation function is data distribution specific, right? Like
yeah.
Or we can like
activation function is empirical. You have to try out many things to find which one works.
Which one works, right? So I cannot be like I was thinking one activation function for every data distribution. Not a good, right? Won't work, right?
Won't work.
So
okay. Somebody in the remote is asking a question.
Yeah, it was me, Asif Madhu. I was just trying to ask. So you're gonna have a paper reading after this? Or
yeah, we'll have a paper reading right after this. So guys, let's take a 15-minute break. It's 4 o'clock. We'll meet at 4:15.
Yeah.
Okay. One other question, Asif. So next week, since you're away, the Tuesday session is not happening. Is that true?
Yeah, we should assume the session is not happening.
The coming week, there is no Tuesday session, correct?
Oh, no. Tuesday session will happen. Only the only the Saturday is not happening. I'm leaving on Wednesday morning and I'm coming back on Saturday night.
Got it. So no paper reading, no weekend session. Okay, got it.
Yeah, no paper reading, no Saturday session. Sunday session will still be there.
You can give more assignments then. Just kidding.
Oh, yes.
And so are you planning, Asif, to like go longer today, or you'll wrap up by 5-ish?
No, I want to. That's why I really mean it. If you guys are willing, I'm willing to go till 10 and teach more.
Okay. So you're planning to go till 10, then I'll come over. So otherwise I won't. So that's why I was
I don't know. It depends upon people's stamina. I am totally ready. For you guys, it's hard. You're sitting in a chair.
Yeah, someone has a hand up here. Anas,
go ahead. Anas, go ahead.
Oh, hey, can you hear me?
Yes, I can.
So I had a quick question about what the input should be. Do you want a fixed vector for all of them, or do you want it to be like a sequence, like an arbitrary length sequence?
No. In this simple example, this is a very simple example of a feed-forward network. It's a single vector or a batch of vectors.
All right, that's what I was assuming. I just wanted to make sure.
Yeah. All right, guys. Let's meet at 4:15. I'll also go drink some water, and we'll meet.
I'm going to be following you on the I am not in that, but I yeah. I'll catch it. This is only like more teaching, right? That is because the original one. Once you go into mathematics, but mathematics studies I do understand. I can multiply. These networks, some networks are switched off in a promote way. You have to reactivate. They have to reawaken themselves. Every time we go to school, we are saying neural networks are great and for neurons. And I'm thinking neurons are the two-dimensional state. There is no three-dimensional state. But the process is actually a third or fourth. Again, multiple dimensions. So this is you can imagine. Even though right now, we get neurons are if you close your eyes and you think about sun is right. And that's imagine down the planet. They are right there in your brain. So this is multi-dimensional right there. I try to analogy. This is the greatest takeaway for today's day. Neurons therefore in hyperdimensions can analogy, visualization of how to visualize कितनी मेहनत की इसमें आपका those are dopamine or dopamine last time and that's what I want to say. Let's say you have 100 dimensions and I think in the end layer just before one minus end layer, right? उस नेटवर्क में सारे के सारे ब्लॉक्स आपके अलग-अलग होते हैं. Then how do you mean एक person you can tell okay this then how I are feeling what you said one more thing put it down. If you forget it. Up the graphic I think I have to stay in last piece. Boundary of boundary is biology is never ending. लेकिन ये भी आप boundary of boundary never ending. He proved it. Boundary of boundary never ending. By the way, you guys are not meeting. You're looking at some results, right? Which one was that? Look good.
Oh, different activation function? Yeah. हाँ वो पिक्चर है वो आप सर्च करें different activation functions different activation functions. Oh, it's just let me glance over it and you will know, remember. Yes, for me. Whatever. Is it you bring this one? That type of. Huh?
So what did you do? Did you already record it?
No, so I can see it preliminary, like smartphone, but now I will be in the top software.
Okay, so next week then.
I don't know. I'm gonna go put it into my Windows machine and try to read out everything. But remember, some data is overwritten.
Yeah, I saw.
That part is gone. So it will try to image the calculation.
Okay.
Right, recover.
Can I just give you like a USB?
No, I will just put it in Google Drive.
Guys, those of you who are remote, are you still with me? Are you having fun?
Yes, Asif.
Nice.
Oh, nice.
Hey, Asif, I was looking at this piece of code,
Mm-hmm.
and in the test loop, we basically say dot no grad.
Yeah, that is the dot eval.
No.
Oh,
There is a with torch dot no
yeah,
grad, right?
yeah. So both of these are good. See, when you put it in evaluation mode and when you say no grad, it is like sort of think of it as a belt and suspenders guy.
No. So that makes sense. But
Yeah.
once we do this torch dot no grad,
Yeah.
I think part of
what
it is
causes it to get activated in the next step?
it's not just about how
No.
Like-
The idea is that
it's also about the type.
the moment you put no grad, you can only go in the forward direction. You can't go in the backward direction.
No, that's fine. What I'm saying is, in the outer big loop, we ran the train
Yeah.
and then we ran the test. Okay.
No. It's not in the test is way after the whole inner outer all loops are done. All of those loops are part of training. Test loop is that, okay, now, like in your case, right? Okay, I've trained a model. Now, how do I check that my model is good? You still have some test data. No? Over the test data also, you want to go mini batch by mini batch. So that is why the test loop, if you notice carefully, it has no epochs. It just has, for XY in data loader, look at this line. For XY in data loader, you make predictions. That's all. Oh, sorry. You don't do any epochs.
No. But see where the test loop is getting called.
Oh, the test loop is just not being called. It is just a function defined inside the class. Somebody has defined this function.
No, it's getting called at the bottom. Look there. Right above the done.
For T, train loop. Yeah. For epoch. Oh, for T in epochs, a train loop, test loop. Yeah. So this is a example that people follow. Here, the wording is really bad. It shouldn't have been called test loop. It should have been called training loop and eval loop. What you're doing is every time you run an epoch, you see how your data is doing on the evaluation data. So let me explain that. I wish this code was not written this badly. Let me explain what happens. But
actually,
would it be okay if I explain it to everyone when everybody comes back?
Yeah, no problem. No problem on that, Asif. But
this is actually badly done. It's very badly written, or at least the naming convention is really bad.
I actually have a very specific question.
Go ahead.
See, now you agree, right? We are running for every epoch. We are running a train, then followed by the test.
Yeah.
Inside the test, we do a torch.noGrad.
Yeah.
What causes us to do the grad when we come back to the next train loop?
Oh, what causes it? There is if you notice in the train, they explicitly put it back into the train mode. Yeah. Model.train is, see, even that method, if I was designing the library, I would have called it set train mode. I wouldn't have called it train. I would have said set train mode. That would be more explicit. Whereas when you call a function train, it looks as though it's training.
Right.
Yeah, it's just badly, open source project has all of these things.
Yeah, that's it.
Yeah. So Satyam, now you feel confident you can do that homework easily?
Oh yeah. But if you didn't do this walkthrough, I wouldn't have been able to.
Yeah.
No, I literally did like this little
Asif, is this Pytorch open source?
Oh yeah, of course. Pytorch is open source. It's a gift from Facebook, Meta. To compete. The other competitor is TensorFlow. TensorFlow is more or less dead. If it is not dead, it's on life support.
Oh, even Google might be using Python.
All of them. And TF started out strong. They had a huge lead. Even now, the lot of production deployments is on TF, but nobody does research on new models in TF. Right? Google is coming up with a new framework that they are emphasizing called JAX. Right? Yeah. And there are other auto-differentiating frameworks. One of them is called TinyGrad. That's taking off. But there is a reason why I don't even mention TensorFlow. I don't want you guys to go start learning it.
So for some of us, where it's practically applied is fine-tuning at the enterprise, right? That's where it is.
Yeah, fine-tuning, training, writing new
models.
Models and training it.
I never really got into it.
So Asif, most of the TensorFlow visualization still works with Pytorch, right?
Yeah. TensorFlow, TensorBoard is the big gift that came out of the TensorFlow.
The other thing I wanted to interrupt, but I felt wasn't right when Prakash asked that question, right? About the scaling up of the dimensions and again coming down.
Yeah.
There was a paper by Hinton which talks about collapsing everything and showing it in one layer. Do you remember that paper? It's a very old paper.
I remember. See, the whole idea is that there was a belief, there was a result actually. I think you're referring to that.
Yeah.
Said, you don't need multiple layers. One layer is enough.
Yeah.
Right. In fact, the universal approximator theorem says exactly that one layer of neural network is enough to be a universal approximator. So
Right.
that
Right.
asked a deeper question then, and Hinton was part of that paper. Then it asked the question, because it was Hinton himself who then went and disagreed with that. He said, yes, mathematically one layer is enough, but the point of multiple layers is you have a more efficient network.
But from thinking perspective, that is good, right? Like you can still
Yeah.
collapse it and make it one layer, right?
Exactly. You can make it one layer. But
And the
because
part
then
is that
intuitively, Sachin, when you
yeah,
think of it just one layer, then you think that yes, you're projecting data in a single shot into the right high dimensional space, and it begins to look very much like support vector machines.
correct, right. That was my next thought where I was saying that the dimension of how much this can hold is so high, but we're just taking a small slice of that high dimension. We are not even making use of it, right?
Right.
We're like trying to like take a wire through a big space, right?
Right.
That's how thin we are using it, correct?
Yep.
Okay, cool.
All right, guys, it's time now for me to past time to ring the bell. Get ready for the bell, guys. Those of you who are remote, can you hear the bell?
We couldn't hear, but let me check. Yes.
Okay.
We heard the word bell for sure.
Okay. All right, guys, we'll take a digression. You know your homework. I would like to go, when we talk about pre-training, I will be posting code just to get you started, but I'll walk you through code. So here's a reading for pre-training, like fine-tuning a model. In Pytorch, I will post just a starter code to fine-tune that. And let's see how much time we have. Today, guys, I would like to have a long session. Next week is off. Right? I will be off. So let me teach you enough so that it will keep you entertained for 2 weeks on this topic. Right. So we will have a longer topic. Anybody has objections or needs to sign off before late evening, before dark? No. I heard no. Clear, loud and clear no. Everybody is fine. Good. So we are now